Thank you. Okay. Alex and I and a few people in the lab were soul searching a bit this morning about how much I should go into the details of trajectory optimization through contact. There's a lot more to possibly say, but I want to at least spend today talking about how do you stabilize those trajectories. I think there's an indifferent and very important view of this hybrid control problem that I would be remiss if we didn't get to cover it. And then we're running out of lectures in this semester. Every time I think, oh, I could talk more about this, I'm going to run off the end and lose something else. So let's at least make sure we talk today about the stabilization problem, given this basic picture that we started last time, which is, I think, a super important picture, maybe important enough that I'll write it over here so it stays up. This picture of the way to think about hybrid systems as having a continuous trajectory that's punctuated by a discrete event with a guard, typically defined in this phi of x equals 0 kind of form, a reset map, and then another continuous trajectory. And of course, you can have another event and another continuous trajectory and so on and so forth. But this was the language of hybrid systems in the way we're using it in this class. And you can imagine that there's a bunch of ways that you could think about trying to stabilize systems that are punctuated by these events, that have contact with the ground, that can cause discontinuous changes in your velocities. Okay, so I want to talk through a few of them and make sure I land some of the big messages. Again, there's a lot. I think I can land the basic ideas, but there's a lot of details that you could potentially look into if you decide to pursue more of this in your research. Okay, so I want to start with the sort of simple version of this, which is the first thing we talked about in terms of analyzing our walking robots was about using Poincare analysis in order to think about the behavior of a periodic solution of a dynamical system. And we'll start back with that and talk about the first way that we could do control as explicitly trying to do stabilization right on the Poincare map. Okay, but to do that, my favorite example is actually not a walking robot, but a running robot. So let me give you, spend a few minutes giving you the simple model for running robots. Okay. And the one I'll use here is the spring-loaded inverted pendulum. Which we like to call slip, the slip model. Okay, so let me even just justify why a spring-loaded inverted pendulum is a reasonable thing to think about when you're talking about running. So the simple models of walking, we're no longer completely happy with this, but we talked about the rimless wheel, right? So the rimless wheel thinks about walking, and the initial, even biomechanics studies of walking described walking as vaulting over your stance foot. Okay, where your center of mass took a characteristic, would sort of go through an apex and then come back down as you were going over your rigid stance leg. Now, I showed you a spring walker last lecture. we were, I think, increasingly sensitive to the importance of flexion in the knee and the springs in your legs even during walking nowadays. So this is a little bit out of fashion, but that's the rimless wheel model, right, is to think about, and the compass gate is to think about going over a rigid stance leg. Running, on the other hand, people think about as being characteristically different, where your center of mass, you come down, your foot hits the ground, your center of mass actually goes down before it goes back up, and you compress your leg significantly. And if things are going well, you store energy in your leg in order to be released again on takeoff. Okay? So running is actually the springs were immediately recognized as being important, and we think about you sort of land, you dump in, and then you jump back out. Okay? So this is roughly, right here, is roughly the spring-loaded inverted pendulum. Okay? Spring, it's loaded as you come in, and it's an inverted pendulum. Now, we're going to make some modeling assumptions I'll be clear about, but basically we're going to assume that there's a rest length of the leg, and when you come back out and hit the rest leg of the leg, you're going to take off. Okay? And then set your leg, come back down, and repeat. So in some strange way, running robots started off as being hopping robots. In fact, all the Mark Raybert hoppers that I've shown you a few times, these were the first running robots. And it's actually sort of interesting that running robots worked well before walking robots did. You would think that walking would be easier than running, but it turns out that at least historically, the running robots started working well first, right? And there's a bunch of possible reasons for that, but when you're being fairly ballistic and throwing yourself through the air, the good thing is you don't have to worry much about what's going on the ground. You're relatively insensitive to what's happening down here, right? If you just kind of throw yourself through the air, then the dynamics are actually pretty simple, and they're not so sensitive to the details of trying to balance my foot on the ground. Maybe the mechanisms were just simpler, right? A lot of times the walking robots were trying to build big articulated legs, and you could just literally use a spring for this, a pogo stick leg. Maybe that's what made it simpler. Maybe Mark Raybert was just the right person at the right time, and the leg lab was just the right person at the right time. But it worked out that running happened first. And we got some really nice, simple models in the running space that are going to help us today. So this spring-loaded inverted pendulum has the same characteristics of our simple models here. So I'm going to give it a rest length L, call it L0 for the rest length. I'll give it a spring constant K. Going to parameterize it with an angle theta. Call the XY position of the mass, of the point mass, M. Gravity G. Okay. Now we're going to assume that the leg is massless, okay? Like we did before, but it's a little weird now because we are talking about a leg that is, there's only one leg. We didn't make a rimless spring-loaded pendulum. We could have, actually, that's been made, but what we're going to assume is that the leg dynamics are insignificant. So therefore, once I'm in the air, I can basically instantaneously change my leg angle to whatever angle I want. Okay, and in fact, my control input is going to be abstracted to be just the orientation of the leg. Okay, but we'll assume a massless leg, and that when I swing this mass, it has no effect on my center of mass dynamics. Okay, we're going to assume perfectly elastic this time. Elastic. Last time was inelastic, but we want to get back up again. So this is elastic collisions. instantaneous impulsive collisions. And so unlike the last model, the rimless wheel model, this time, remember the rimless wheel lost energy every time its foot hit the ground, and it gained energy by falling down a ramp. This one is actually, energy is conserved. There are no energetic losses in this system. As such, it's going to be able to run on a flat ground, okay? And you should be immediately suspicious about whether it could possibly be a stable run if energy is conserved. Normally, we actually relied on the dissipation of contact in order to stabilize the limit cycle before. This time, energy is conserved, okay? All right, so my coordinate system is, by default, is x, y, and theta. It's still hybrid, right? It still has that same picture of having this impulsive event, right? It's just that it's now an elastic collision. So when my foot hits the ground, I'm going to instantly change my dynamics, where the dynamics in the flight phase, right? I'm going to actually break up the dynamics into the flight phase, which is just a ballistic path of my center of mass, right? Just the ball flying through the air. Then I'm going to have a touchdown phase. As soon as my foot hits the ground, I'm going to assume that when I'm in the air, my leg is at rest length. So I can know the kinematics, and I know the condition when my foot suddenly comes into contact with the ground. I'm going to switch the dynamics. I'm going to assume that I have a pin joint at the ground, that my leg begins to compress, and I'll go into this, this sort of characteristic spring-loaded inverted pendulum dynamics. And like I said, when I come back out, the leg will extend until it reaches its rest length, and then we have this takeoff back to the ballistic flight phase again. Now the rimless wheel, I said, was this beautiful system. It's the last system that we'd be able to plot everything about it, right? That we could put everything in just a one-dimensional map. We could draw its basins of attraction. It was great, right? With a few caveats, this is the other system that we can almost do that with, okay? The rimless wheel, we actually could even closed form solve for the return map. Like, we had everything. We're not going to be able to do that here without some approximations. But in fact, we can get this to be a simple map that we can draw. It's Poincare map. And the reason for that is that, okay, so why is that seem something that might be too hard? Is that by default, I actually have a lot of state variables flying around here, right? Potentially 6 to worry about. And if I want to have a map, I know my map is going to remove one of those, because I'm going to take a surface of section, an n-1 to surface of section. But that still looks like I'm going to be in a position where I need to plot 5 variables evolving in time. So how do we get it down to less than that? Okay, so here's the trick. X, the dynamics are invariant to X. So if I were to look, what we're going to look at, we're going to define the Poincare map to be from one apex, so at the top of the bounce, to the next apex. At the apex, the dynamics that I'm going to, the dynamics from one apex to the next apex, the X dynamics sort of can be safely ignored. They're just going to be, I'm just going to be moving forward I could do a strict translation in x and my dynamics would be the same. Okay. Y matters very much. That defines my apex. But at least the apex is defined by y dot equals 0. Right, that's what defines my map. Theta and theta dot, by virtue of having a massless leg that we can set to be arbitrary, we're going to effectively rule these out. Because by this massless leg assumption, we're going to be able to place that wherever we want, so the dynamics are not essential to my Poincare map. Getting close, okay. This one's 0, okay. So now I still have y and x dot. What can I do to reduce it? There's one more observation I need to be able to be completely satisfied thinking about evolution in just a single variable. Why is my hopping robot, if I know, let me say it even this way, if I know x dot, I know what y has to be.
Well, because of conservation of energy.
You got it, right? If I know energy is always conserved, then by conservation of energy, when I'm just a ball flying through space, if I know x dot, then I know y. Or if I know y at the apex, I know x dot. Okay? So we'll do a map from y to y at the next step. You could similarly do x dot to x dot at the next step, but we'll do y, just a map from y n plus 1 through a Poincare map. This yellow chalk that he sometimes writes with bugs me. Okay. So this is the step-to-step apex to apex map for the rimless, or for the, sorry, spring-loaded inverted pendulum. Okay, this time I can't actually integrate it in closed form, right? You should think about what this p is hiding is actually an integral from the time of collision, the nth collision to the nth plus 1 collision of the continuous dynamics, right? And in the rimless wheel, I was actually able to integrate that in closed form and get a closed form expression for p. But more generally, we're rarely going to be able to do that. Even the Van der Pol oscillator, I couldn't do that. Okay, but I can numerically evaluate p. I can run a bunch of simulations. Or you can do small angle approximations. If you assume that you came down fairly close and just went through a small angle, there's a linearization that you can do there that does a fairly good job of reproducing this. Okay, and what you get is this sort of beautiful solution here, which, if you remember, the line of slope 1 is an important line for these discrete maps. So if I say the y at the nth step to y at the n plus 1 step, I get this curve that looks like this, okay, where I have actually two fixed points. This one is unstable, and this one is stable, where if I were to do my little iterated map trick, it converges. It doesn't necessarily monotonically converge, but it will converge to the stable fixed point. Now that's a little bit weird for me to suddenly say I've got a stable fixed point when we said you should immediately question whether stability is even a possibility. And the reason that this appears to be a stable fixed point when I do this integration is precisely because of this trick we used in the last step there. By enforcing the relationship x dot and y here that implied that energy was conserved, it sort of hard-coded a conservation of energy. So this system in fact, is not stable in perturbations in energy. If you were to push it in a way that increased its energy or decreased its energy, it would keep that higher or lower energy for all time, okay? But because of my projection down to the one-dimensional map, projecting it back to the energy equals my original energy, I've now made a system that is stable in those coordinates, okay? So it's actually, when this started coming out, this got a bunch of people, even sort of more theoretical physicists and applied mechanics people, excited because you shouldn't be able to get stability from a conservative system. And they wrote a handful of papers about piecewise holonomic systems. Having a form of partial stability, exhibiting these systems that in every piece, they're conservative, but the reset maps can do tricks in perfectly reasonable ways, can do tricks that just having an event in the middle of an otherwise conservative system is enough to give it forms of stability. Okay. All right. So what does that actually look like? Here's my down below the rimless wheel and the compass gate. We have a little spring-loaded inverted pendulum model where I just typed in both the visualizer and the equations of motion. It's maybe worth mentioning, this is another example of trying to type in the hybrid dynamics, where I declare the witness functions. That's what simulators call the guards, okay, witness functions and the reset maps. So I have the dynamics of takeoff, of leg compression, of touchdown. I have all these little computations, and I say an event happens when there's a touchdown event, there's a takeoff event, there's an apex event. So if you want another example of sort of using, declaring a hybrid system, this is a reasonably simple and good example. And this is what it does. So I pick some initial condition, I pick some stiffness of the leg, I give it some initial position and velocity, and I simulate it, and it runs stably, okay, with that projection trick that actually, from small changes in initial condition, it will converge to this, this hopping, steady state hopping. Okay, and that was the model that, combined with the compass gate, gave us the models that were spring mass walkers, which was kind of a nice putting it all together. Any questions on that sort of simple model? I did that quickly, but we're going to use that now. We're going to understand how to control it. If we want to change how it's hopping, this is like a beautiful example of what we're going to do for control. If it was a slope, then the energy would no longer be conserved. So it would, we would need some sort of dissipation to have any form of stability there, I think. It would just go faster and faster and faster if it was down the slope. I mean, you can make small changes to these initial conditions to get pretty hilarious animations out of it, going bang, and like shooting itself off backwards, or face first. And I think it would just happen faster on the downward slope. That's good. Any other questions about slip? Yeah.
Yeah, so here you're assuming that the leg is not slipping, right? Like it's always meeting the ground so that the spring is compressed, otherwise you wouldn't conserve energy.
Correct. So it's actually even an instantaneous moment. Let me repeat the question just for the cameras. But yes, we made assumptions about sort of no slip, but the reason I didn't even say slip was because it's only instantaneously on. That's not true. Sorry. It instantaneously comes into contact. You're right. And then we make a pin joint. So there is a no slip assumption while I'm in the stance phase. That's correct. Yeah, I basically make this into a pin joint. So there is a no slip assumption too. I should write that here. No slip. Good call. Okay. How do we think about control for this system? Okay, so you saw what it looks like here. We're hopping along. The control decision that we have since the leg is massless, is that every time we're in the air, we get to decide instantaneously what's going to be the orientation of the leg. Okay? So the control decision is the touchdown angle of the leg. And our job is going to be to design that touchdown angle in order to achieve some sort of, control over the periodic solution. So if we were to be more explicit now about this Poincare map, we could write it as y is n plus 1 is some discrete map integrated over the cycle of yn that's dependent on my control, my touchdown angle control. I drew it there for a fixed choice of touchdown angle, but I could actually choose a different angle at every step and potentially change the rate at which it converges, even make a new, move the fixed point. I can change that map by changing my touchdown angle. So our goal should be to come up with, a reasonable goal in this formulation would be to come up with some policy, right? This looks like everything we've written before, okay? But understand that this is somehow like a temporally extended, decision where this is one control decision per cycle. And by the way, if this offends you, this notion of like having the ability to make an instantaneous control decision and really only having one decision per cycle, I would say that this is how robots are being built these days, right? This notion of having this is a Spot Mini, this is Mini Cheetah, right? But characteristically, these robots have a relatively significant mass and inertia around their body and these super light legs, right? And in fact, the dynamics of the legs are you can almost put them instantaneously. And I think as the robots, this is just two of my favorite, but a lot of robots look like this now. A lot of the quadrupeds look like this. And once they started looking like this, they all started looking like this because it's a really good idea, right? You sort of can't fall down if you can move your leg arbitrarily fast, right? That's one of the reasons I think quadrupeds started working so well, is because we got better actuators and faster, lighter legs. And really, yeah. Whenever you start falling, you can move your leg there, and now you never fall down. Okay, so this is, I think, this simplification of thinking, reducing your control decisions to like, where am I going to place my foot, or what's my touchdown angle, is not so far from reality, I think, as what you might think. Okay, but it does lift this problem, and sort of, it's not a trajectory over time. This is once per step. Okay, and there's a couple natural ways that you could do this, right? So here's a reasonable approach. We could linearize P, right? So we could say that yn plus 1 is approximately equal to partial P partial y, evaluated at y star, u star, whatever. Right, and do LQR. Right, this is just a y bar plus b u bar. This would be discrete LQR. want to make sure you realize that you can do that. We're going to have better, for this system, we're going to have better ways to do that. But that tool would completely work, right? It might be more local if the linearization's, bad. But actually for this, I think it would work fairly well, right? The trick in doing this is that since I don't have P in an analytical form, getting that gradient is actually, it's like the backprop through time that we had to do. It's the adjoint equation, for instance. It would be solving a gradient backwards across the trajectory in order to compute the gradient of the entire map. So these would come from adjoint equations, where we take some care to handle the impacts in a way that I'll show you before the end of this lecture. Okay, but you can get this numerically. Some of you will prefer to call that backprop through time. But that's just that's the only trick. Otherwise, LQR basically works. Which is kind of cool, right? To make discrete decisions in a way that's abstracted from time. The duration of that decision is not even set a priori. If I make a different choice for my touchdown angle, I could spend a different amount of time in stance, right? So it's really not any standard discretization of time. It's time abstracted. And LQR can still work on that map. Rich Sutton always used to complain that control theorists never know how to abstract time. And I always disagreed. So Lyapunov functions are a great way to abstract time. Poincare maps are a great way to abstract time. There's lots of good tools for abstracting time. Okay, here's approach number 2. We can do deadbeat control. What is deadbeat control? I mentioned it once before when we were talking about discrete time systems, but you guys remember what deadbeat means? If I have a stabilization problem and I'm trying to get to the origin, LQR is going to take an exponential convergence to the origin, right? Even LQR in discrete time will get exponentially closer on each step, but it's a linear map. In discrete time, though, I can actually just get to the origin in one step, right? So a deadbeat controller would mean in a single discrete step, I obtain the origin exactly, okay? At the desired fixed point, right? So that's a little interesting. I mean, so I don't want to say that that continuous time systems. I want to not say that continuous time systems can't do that, but this would be equivalent to a finite time convergence of a continuous time system, which is possible. There's a different branch of controls that thinks a lot about that. But this is something that's more natural in continuous time, or it's in discrete time, right? So if I think about, in fact, the limit of the LQR problem, where I remove the cost on control actions, then the thing I should do, so in continuous time, that would be bad. That would turn my gains up to infinity, right? In discrete time, you can actually just arrive at the goal with finite cost in a fixed amount of time. Okay? So if for any x, let's say 0, I could choose u0 such that p of x0 u0 is x desired, let's say. So that map has to have some certain properties. It turns out that there's a paper that I cite by Hartmut Geyer and others that shows that this particular apex to apex map for the slip model has this property of invertibility in some sense, right? So that for any, in the domain where the energy is fixed and your leg is not horizontal and it's not completely invertible for any possible x desireds. There's some x desireds that you don't have enough energy to achieve, but in some important operating regime, this map is effectively invertible. And that is that you can give me x desired and x0 and I'll solve for the u that will achieve it, okay? And that's an extremely cool observation that is a little specific to this, but this notion that you can achieve deadbeat control for discrete time systems is important. Okay, does that make sense? Yes, sorry.
Maybe a bit of a story. What's the point we're linearizing around the LQR approach?
Yep.
The
So it could be it depends what your control task is, but if you want to just stabilize, like increase the rate of convergence to the nominal limit cycle, that would be fine. You could potentially also try to stabilize a point that wasn't originally a fixed point on the Poincare map. So you could imagine it as being a desired hopping height. You could linearize around that and turn an unstable hopping height into a stable one. Yeah, so y star would be your desired height. Mm-hmm. Okay, now there's a really remarkable result in slip control that is the reason I like it as the example. It turns out that the inverse map here, which goes from x n and x desired to u n, has a certain smoothness property for this system, okay? So that if I were to change the desired height a little bit, then actually my control changes a little bit. Again, in this reasonable regime of operating. Okay? Now, here's what's amazing. If you extrapolate that observation, then what this means is that you can effectively, this hopping robot can run blind on rough terrain with a deadbeat control coming out. Okay, there's a few steps required to get that, but just take a second to appreciate this. This is saying that if I have a hopping, if I'm in my current hopper, I'm going to run on rough terrain here. I want to achieve that every hop comes back to the same apex, or equivalently, the same running speed. I want to say, no matter where the ground is, I'm going to bounce, and I want to come back up to exactly the same height every time, or to the same speed, right? Because those are. So what's the trick here? The trick is that this depending on the relative height here, I will choose a different stance touchdown angle. Okay, so the function, if I knew the height to be at this relative size, that would ordain a particular touchdown angle. If I knew it to be at this height, it would be a different touchdown angle. But all of those I can compute. And it happens that it's a smooth function. So what I should do is I should put myself as if the ground was way up here. I should put myself in that angle. If the ground happened to be right up there, I'll be in the optimal deadbeat controller. And then as I fall through the air, I'm going to continue to sweep my leg in such a way that whenever I happen to hit the ground, I'm going to be in exactly the right touchdown angle, so that on the next height, I'll have the deadbeat solution. This is sort of amazing, right? That we can have open loop. Okay, it only depends on time. I can just have the time recorded since I left the apex, and I can just sweep my leg through a pre-observed schedule. Open loop, it's going to be deadbeat. Always gets me exactly back to the desired height. Blind, it doesn't observe the height of the terrain at all. Running on rough terrain. or uneven terrain, if you will. Those words you wouldn't expect to be all in the same sentence. Yes?
Does it still need to have some sensor to determine when it hits the apex?
Yes, good, good. So it does depend, it's clocked on the arrival at the apex. So just knowing that velocity change direction, yes, exactly right. But during the cycle, it's open loop. Awesome. That's pretty good, right? I did it in the wrong order. So here's the Hartmut's render of this open loop, stable, running, hopping on rough terrain, right? Now, there are all kinds of cool experiments of animals that do like amazing things running on terrain. I should have put it in actually. There's a great video that by Monica Daly who studies guinea fowl, okay? And she has like this great experiment where there's a treadmill or there's like a board, there's a guinea fowl running across the board. In the middle of it, there's a sheet of tissue paper with a hole underneath it, okay? So the bird has no idea that there's actually a hole there. It steps its foot down there and basically does this. Like it just, you can watch the guinea fowl run across the treadmill unperturbed. You can watch it with the tissue paper. Its foot drops like, half a leg length or something, and the center mass like never changes. It's just, the legs just going up and down, or whatever, and the center mass is great. So animals kind of do that, and especially the birds that have super light legs. I think there's also a couple outtake videos where they didn't do that, but it's pretty amazing. The other great thing about SLIP that I have to tell you is that it's proven to be like a pretty good model actually of the dynamics of running across many different orders of magnitude of animals. So if you look at just the center of mass dynamics of animals as they run, they tend to have this sort of spring-like behavior, okay? And the dimensionless stiffness, if you sort of scale the stiffness according to the mass and take out a dimensionless quantity, then actually not only does the spring mass model describe it fairly well, but you have this characteristic stiffness that goes from like a little cockroach, all the way up to humans and kangaroos and horses, I think was maybe the biggest one, okay? And they have all kinds of different gaits, different numbers of legs, okay? But they all have this sort of characteristic spring-like gait, not just that, but that it's a similar time constant, scaled, right? Pretty crazy, right? This is a big thing in comparative biomechanics. Okay, and it inspired a bunch of other experiments too. So my favorite one, I promised somebody the other day that I'd show this video, but it turns out it can sort of explain the lateral stability in some of these animals too. So there's a lateral leg spring model that just sort of describes the lateral stability of some of these animals. And this is one of the better videos of all time. They studied the cockroach's stability mechanism, okay? And Devin Gendrich is the one who did this experiment. He told me all about it. So he said, first of all, it's kind of annoying to try to measure ground reaction forces of a cockroach, right? Because you don't have force plates that small, right? Like, how are you going to measure this, right? So he came up with this really inventive technique where he would like put Jello down, and he would put basically a diffraction grating on the top and the bottom of the Jello. And when the foot of the cockroach bent the Jello, it would bend the light, and he would be able to make a force sensor out of this, and apparently feed the cockroaches. He said, like, he could tell you exactly what flavors of Jello the cockroaches like and don't like, and he found the one that was like, lasted the longest. Okay. But then he said we started trying to understand their stability, and so we needed a way to perturb the cockroaches. And he said it was really hard to come up with a way to like make a fast enough perturbation. These guys' legs are flying, along. How do you come up with a fast perturbation of a cockroach that would like perturb their center of mass so you can watch sort of this instantaneous thing? And the solution he came up with, which I'll show you on the next slide, he was nice enough to share the video, is he eventually, he tried to tie a little string around, pull him, but he just couldn't do it. So he eventually found a small cannon, and he basically bolted the cannon to the exoskeleton to the back of the cockroach. And I mean, they're cockroaches. He got permission, he put the small cannon on the back of the cockroach. And this is a high-speed video slowed down of the cockroach running along. I think you'll know when the cannon goes off. Okay, instantaneous perturbation. Actually, this one got 2 perturbations because the ball came back and hit the cockroach again, okay? And this led to a series of experiments where you could understand the stability properties of the cockroach. That was awesome. And the conclusion of that actually was super interesting too, was that even though it took a few steps for it to regain its total yaw, it took a few steps to reorient, its center of mass velocity was recovered inside a step, right? Like faster than could be explained by the neural connections from the leg of the cockroach through the spine, whatever it said, and back, right? But there's like wasn't enough time to go through the few synapses it has and get back. So he argued that at least a part of that stability was coming from the mechanism, the mechanical design, the musculature of the cockroach. Okay? Pretty fun video. So that's how you do stabilization. Yes?
As I recall, he had a great name for this device.
I don't know the name of the device. What's
the RIP apparatus.
The RIP apparatus, okay, yeah.
Rapid impulse something.
The only rapid impulse, right? I wonder how many, he also did tell me, so he says, he said RIP apparatus was the name of it. And he did tell me one time that it's surprising how little gunpowder you need for the experiment. And that just, he never said more than that. But I kind of thinking, how many, like, just, it suggested that there were some flawed experiments that started off with too much gunpowder, Okay, good. So let's generalize this. So, this was the stabilizing the Poincare map, but I want to bring it back to now doing continuous control decisions where you could not just fix one control for the entire cycle, but actually try to continuously control, change your torques, let's say, over the duration of a cycle. You would expect that to be a richer class, right? And you could do it in this framework. You could say, for instance, I'm going to parameterize my leg angle as a spline and just reason about it on the Poincare map. But that would prevent you from making updates inside the cycle, right? You want feedback to come in as I move through the cycle. I'd like to be able to update my control decision. So on to hybrid LQR. And I should say that I lean heavily on LQR in these, in these lectures because it's the one we talked about. I would say most of these things, I would almost be happier calling it linear optimal control, right? Most of them are not particular to LQR, but they are particular to the notion of trying to reason about the local linear dynamics of the system and then doing something that we know how to do well from the class of linear optimal control. So the same thing's true here. I'll do LQR because we know it. All right, so in my picture here, we already know how to do time-varying linearizations and get a time-varying Riccati equation and then therefore a time-varying LQR solution, okay? And it turns out we can do that again here with, of course, a little bit of care required to handle this part. But it turns out that the thing you want to, you kind of hope would be true is true, that if I were to approximate this with a time-varying linearization, and this one also with a time-varying linearization, and let me call this moment of collision on the nominal trajectory. I'll call that my time of collision, TC, and the moment right after, I'll call this TC minus, and this is TC plus. Those are instantaneous collisions, right? I can call this, let's say, time 0, and this time final. What I'd like to do is come up with like a finite time, finite horizon LQR strategy that works for this now hybrid system. And you can imagine that it must be that since this is a continuous trajectory here, that the way I'll start is by the same way I started with the finite horizon LQR. I'll start with a final condition on my Riccati equation, and I'll integrate back my Riccati equation at least to here, okay? This is the continuous differential Riccati equation backwards from T final to TC plus, okay? And then it turns out, if I make another linearization of the collision here as x bar, I could put a control input there, but I often don't because zero time passes there. So you need some, I mean, you don't have time to make a control decision inside here. If you have something like the push-off event at the toe that you've somehow engineered your system to make that split-second decision, then maybe that's a reason to do it. But oftentimes I think of this as being not a function of u, only a function of x. Okay, but it's certainly a function I can linearize. Bless you. Yes?
Would it be valuable to say, stick an input there when you're trying to design your system and say you want to know what compliance you want there?
I see. Totally. Okay, so the question is, what if I were to think of it as a design parameter? Yeah, so for instance, if I wanted to design the stiffness of my leg or something like that, you absolutely could. So there are different gradients that you could take through here. For instance, to take a gradient with respect to some parameters, where you would include gradients in there, absolutely, yes.
I imagine humans have some control over that, how stiff our feet are.
So I think of, so the question is, do humans probably have some control, right? Yeah, this is a limit which is too stiff, too instantaneous for what's really happening in the real world. I think humans actually have relatively slow collisions and time for those things to happen. Well, I mean, there is an instant of collision, right? So if you run on a treadmill, you will see this characteristic. This is straight out of the barefoot running literature now, okay? So if you run on a treadmill and you look at your ground reaction forces, for a standard person wearing shoes, you get this like instantaneous spike at the moment of collision, and then you get sort of the standard stance gate. This would be over the duration of stance. This would be a ground reaction force from a load cell, okay? And the claim is if you take your shoes off, it looks more like that. I mean, it's still a little bit like this, okay? But there is this impulsive event at the moment of touchdown, which I suspect we don't have much control over, right? And this is heel strike, typically. And yeah, I would guess we don't have much of a chance in that. I mean, part of, Sangbei's been trying to like talk about how do you do at least proprioception of that with fast enough actuators and current sensing and the like, and maybe a little bit of control, but that's a pretty fast event. Great question, okay. It turns out that the thing you need to do to continue to back up your cost to go across this jump and get back to the other continuous part we know and love is that step 2, which is right after heel strike, sorry, is to apply one step of the discrete Riccati solution across the reset event. And then integrate, again, continuous, the Riccati from TC minus to T0. That's what kind of you'd hope to be true, and it works out that this is called the jump differential equation, the jump Riccati equation. with one big caveat, it's sort of the right thing to do in the linear optimal control sense. The one big caveat is that, I'm going to get my colored chalk, but I refuse to use the yellow chalk that writes permanently on the board. Imagine I'm trying to converge to this trajectory, but I'm not on the trajectory. So I've got another trajectory that's coming in. Okay, it's near the trajectory, but it's not on the trajectory. The problem is that I land at the moment TC, I may not be exactly on my foot might not be hitting the ground. I might not be exactly on the guard. Okay? Which means that the linearization that I use of that reset map is going to be a little off, potentially. For this cycle, immediately, it could be doing the very wrong thing until things catch up. Did I say that well enough? If I'm clocking my linearization only off of time, the linearization I'm using for control, and that linearization changes discontinuously, then if I'm on the wrong side of the guard using a different linearization, then my linearization is not valid. Okay? So this recipe gives me a controller, u bar equals negative k of t x bar. But that controller could actually do the wrong thing at that right around that squirrely moment of collision. This is real. This is a real problem. Like, for many years, and maybe still today, you can ask the people that have been playing with mini cheetah and the like, but a lot of times, actually mini cheetah, the legs are light enough, I doubt, but we would actually turn our control gains artificially down towards 0 right around the moment of impact. It's like this dirty little secret in all of our papers, right? So we'd have our robot, we'd have this beautifully designed controller, it was optimal, whatever, and we kind of turn it off right when the foot's going to hit the ground, and then we wait a second and we turn it back on, and that's all good. See, no, you didn't see anything, right? And it was because of these kind of details. Not only those kind of details, but if you think about I put a video in actually of one of our old robots that did this. Yeah, this is an old compass gate robot, very old actually. And before the toes were working, the trick is you walk on blocks, right? So if you can't retract your legs yet, then you walk on blocks. Okay, so this is what walking robots used to look like. That fell down at the end because the cable was not long enough, not because it was unstable. But this particular system is the one that inspired me to think about the next ideas I'll tell you about. Because the only actuator here was an actuator, in the compass gate was an actuator at the hip. The way that you want to stabilize a trajectory implies applying a torque at the hip. And the sign of the torque at the hip is exactly opposite if you're in collision, if you're pre-collision or you're post-collision, right? If my leg's is not on the ground, then I'll be applying potentially a torque to keep my leg up, for instance, so I hit my desired stance angle. The second I'm down, now I'm supposed to be applying force on the ground to pull myself forward, and it can cause, not always, but depending on the nominal trajectory, it can cause an absolute sign flip in the torque. And the consequence of not dealing with this properly was that you'd have things like, you'd get down, the robot would think it's in contact, and it would, like pull its leg or throw its leg, right before it hit the ground. It's like the time that you want it to be rock solid, like I'm going to hit my foot placement, I chose my foot, and then it's like it stepped on a banana peel, right? So that inspired some work that I think is a satisfying resolution of this problem. Okay, and it goes with this transverse coordinates and transverse stabilization. So let me tell you that story. a short version, a medium version, and a long version. So I'm looking at the clock, and I'll give you the medium version. Okay, so the big idea of the transverse coordinates, it came from Anton Shiryev and others, and Ian Manchester is the person who I was working with, who he came from Anton's group to our group and taught us all about these things, was this idea of working with a moving Poincare section. I guess it was even Chris Hauser before that. Not Chris Hauser, John Hauser. Okay, so it turns out you can do Poincare style analysis, but instead of having the Poincare map stuck at, like, say, the apex or something like this, you could think about having still a surface of section, but have it ride along the limit cycle, for instance, in a way that can still tell you something about orbital stability, as opposed to trajectory stability. Right? Orbital stability, I tried to make the point, was an important thing. So let's just take a simple ring oscillator. Okay, so imagine I just have two variables. Okay. Imagine this is my sort of nominal limit cycle, and I've got a nice stable convergence to this. And to introduce this notion, just like I introduced Poincare, I'm going to actually just talk about how do we understand that this is stable first, how do we analyze its stability, and then we'll extend that back to control design. Okay, so how do I analyze the stability of a simple oscillator? The solution I gave you so far was to have a single surface of section, the Poincare map, and analyze its dynamics as it, each time it visited. And what I'm going to do now is allow my surface of section to move, to have sort of a phase relevant. Okay, that's as long as it's not real, yeah. I'm going to have a moving surface of section that moves along the orbit. Okay. What's important, just like the question, Zev, I remember you asked about the transversality condition on the original Poincare map. We're going to have that same condition here. I'm going to choose a coordinate system, and the one rule of the game, an important rule of the game, is that when I choose my moving coordinate system, I'm never parallel to the trajectory I care about. No glancing collisions. I don't have to be orthogonal, but I do have to be transverse, which just means non-parallel. So it's going to be a transverse coordinate system. It turns out that if I were to define a transverse coordinate system as a coordinate system that's a function, let me rewrite. I have x1 and x2 as my original coordinates. Let's write the transverse coordinates as the transverse part plus the phase sort of in the trajectory. I'm going to have my split. I'll have a map that goes from x1, x2 into a transverse coordinates. Okay, and similarly, I'll actually have a map defined in both directions. So for given any x1 and x2, I'm going to pick my tau by just looking, for instance, at I just put it in polar coordinates for this example. I just put my polar coordinates, call one of them the angle tau, and the radius, the length, x perp. Okay. What's interesting is if you rewrite the dynamics in these transverse coordinates, you can certainly do that. You can write I can just take my original dynamics in x1 and x2, apply the change of coordinates, apply the derivative of the change of coordinates. I want it to be a smooth change of coordinates, so I can make this map exist, okay? But I can rewrite the dynamics in this coordinate system. It turns out that if I can establish stability of just the transverse coordinates and put minimal or no assumptions on this, then that is equivalent, that gives me the ability to talk about orbital stability of that trajectory, of that periodic solution. It makes sense, right? But it needs to be established that you can write a Lyapunov theorem, for instance, that says that if I just show that the blue directions are stable, in some sense, that implies orbital stability of the red trajectory. Okay? Is that concept clear? I mean, in pictures, we can make it more careful, but do you see the goal there? Just write the, if I were to turn x1 and x2 into polar coordinates, I'll call them r and theta, for instance. Where r is x1 squared plus x2 squared square root. Theta is just a tan, whatever. Okay. As long as r is stable, if r converges to 1, for instance, in this, in this particular picture, then that implies that the original system is orbitally stable, right? The concept of orbital stability is that I'm stable to the manifold, but I don't say anything about stability along that manifold. So it's exactly, I think it's exactly what you'd expect, and I just hope my notation isn't getting in the way of that. Ask questions. Okay. It turns out I can write a Lyapunov theorem, right? I can talk about Lyapunov in the transverse coordinates. The argument is roughly if I can find a positive v such that for all tau, vx perp tau greater than 0. I'm using my shorthand. This is the middle length treatment here. But I could take x bar in some domain if I want to talk about local stability. Okay. If I can find a v that's really it's just like when you could think of this almost exactly what we wrote about time-varying Lyapunov functions before, right? So it's now a tau-varying Lyapunov function where it's a positive function, its derivative is down. When I say positive definite here, that implies that when x perp equals 0, vx perp tau equals 0, x perp not equal to 0. That's what I mean by the positive definite notation, right? If I can find a function, which is really kind of essentially, it's a time-varying function of these in this r coordinate, in this transverse coordinate, then this implies local asymptotic, in this case, orbital stability of the trajectory defined by x perp equals 0. Again, I think the idea is not surprising. The mechanics of it get involved, and I'm not giving the worst of it. But if I'm collapsing in blue, then I'm orbitally stable in red, right? So let's compare this type of analysis with if I were to work directly with the original Poincare map, which was stationary. I could do, I said we could do a Lyapunov analysis directly on the Poincare map. The reason that would be hard to do is that in the original P, to establish that V was going downhill on every visit to the Poincare map, that would involve integrating over the Poincare map. It was not a simple, I don't have any closed form evaluation of the Poincare map function P. This check, these conditions can be checked by just checking the instantaneous derivatives of the equation. It's a much more actionable way to discover a Lyapunov function. If this is satisfied for all x, it's an instantaneous check. I don't have to integrate across the cycle. So that's the big difference here, but the result it gives you is the same. They both imply something about the asymptotic orbital stability. Okay. This observation sets on a cascade of results that becomes incredibly useful all the way up to control design. So there's a notion now of a transverse linearization. Which, for instance, which is precisely just linearizing the transverse coordinates here. Since x perp I've defined already to be at the origin, I'm not writing a bar this time. I'm saying x perp equals 0 is the origin, so it's my desired solution. Okay, so I can linearize the dynamics in that blue coordinate system, right? And I can use this, for instance, to find an initial Lyapunov candidate. Remember the way we found a Lyapunov equation? You know, we solved the Lyapunov equation just to find a Lyapunov candidate to prove stability. I can now use this to find a Lyapunov candidate. In the steady state, it was just PA plus A transpose P equals Q, whatever. You had it on your midterm, right? So now it's just P dot. It's the same thing, but it's a periodic solution. With so if I can find myself a positive definite, or a symmetric positive definite matrix here, that's a solution to this Lyapunov equation, differential equation. It's a periodic solution. Then that gives me a Lyapunov candidate like this that I can use to establish a, you know, that's a mechanistic way to come up with an initial Lyapunov, quadratic Lyapunov candidate. Yes?
Shouldn't this be negative P dot?
Yep, thank you. I missed a negative on this side. Thank you. Okay. So what does that picture look like? I think I have it here, right? So around a limit cycle, you know, you're going to have a kind of a bowl, a quadratic bowl, whose origin is at on the cycle, right? And this is my initial guess for a Lyapunov function, which I can then verify. We can verify with sums of squares, for instance. You can estimate a region of attraction with sums of squares. All of those tools hold. Am I radioactive? What happened? That's cool. Okay. Okay, and guess what? You can do the same thing for LQR, right? You can do LQR in the transverse coordinates to establish orbital stability. Okay, so what does it mean? What's the difference between doing LQR in the original coordinates, time varying, versus LQR in the transverse coordinates? The time varying LQR in the original coordinates, if you perturb it along the trajectory, it will try to fight back. It will try to stabilize phase and out of phase, right? Both r and theta in my picture before. If I do LQR only in the blue coordinates, in the transverse coordinates, which is going to be in general in n-1 dimensional coordinates, then I can stabilize the system in a way that if you were to push it along the trajectory, it will not resist. Okay? It also has an incredibly good benefit in the picture I've been using all along here, is that I can choose a transverse coordinates that's transverse to the trajectory, but also one which lines up beautifully with the guard and my reset map, so that quirk I had about trying to worry about what's happening if I'm on the wrong side of the guard is gone. I have a complete and well-defined mapping, at least in the linearization of that guard, that defines from this state which time, effective time, I should be applying the controller from. This is almost the same as just saying I'm going to do the normal LQR, but I'm going to just, you know, wherever I am, I'm going to find the closest point on my trajectory and use that control. A lot of people want to do that. If they just design a normal LQR in the full coordinates and then just say, well, I'll take, you know, I won't follow the rigid time schedule. I'll just look up where I am at what's the best time to use. But if you do it after the fact, you haven't told your synthesis about it, you can actually get, even for systems that are exactly have a time varying linearization, you can actually get unstable solutions like that. And you should think about the transverse coordinates version of LQR as exactly the form of LQR that is robust to that projection. So this is the right thing to do, is to not design K in the full coordinates, design K rather only in the transverse coordinates. It's also just a better thing to ask. You're asking your controller to do less. If you find the time-varying LQR for the compass gate in the full coordinates, it'll tell you there's an extremely high cost to go and requires large actuation, or even, it might be that you can't, that it would be unbounded. But in the transverse coordinates, it's very well behaved. You're not asking this one actuator to try to catch up in time, which it just can't do. You're asking it to stabilize one less dimension. And in the limit, there's an important limit where your walking robot, for instance, has under actuation just degree 1. So you could have a large, complicated walking robot, but if you think there's sort of the only degree of under actuation is, if you have actuators at all of the joints, except for maybe you've got a point foot, you could argue in the plane that that's under actuation degree 1. And stabilizing, orbital stabilization, stabilizing the n-1 coordinates, is actually almost a fully actuated problem. You can just do PID control. On the other, you have to do it in the right coordinate system, but you can stabilize that very easily when you have n-1 actuators and you're trying to stabilize n-1 degrees of freedom. And that is what, if you've ever heard of hybrid zero dynamics from Jesse Grizzle, there was a very successful series of walking robots from Michigan, Jesse Grizzle and other people, where they've got Cassie doing it now, but this was, the reason I picked this video was kind of, this is Marlowe, I believe, that was in the intermediate. Watch carefully what's happening here. So first of all, the poor guy didn't get a full circle to work with. That was, he's got like half a lab, right? And that's just time lapse, forward in time. Okay, so first of all, it's very stable. But second of all, the way he resets the robot is he just pulls it backwards. Okay, so in the picture that we have here, what's happening? They're explicitly not stabilizing in phase. So what he's doing, actually, he's just walking up. And even though the robot, by default, wants to walk forward, he's just pulling it backwards, and it's just going, it's like a clockwork man, right? It's just being pulled backwards along the cycle, and it's stabilizing all the other coordinates in the relative, it's probably going to say silly things. But it's just, so it does its nominal gait, it's looking up where it is in time, it's figuring out what its other joints should be, it's just doing its good walk. And then he pulls it backwards, and it's like, okay, I'm going to just go backwards up the cycle, and it's completely, there's no attempt to stabilize along the cycle. And it's an easier control task. It's less to ask of your controller precisely because you're stabilizing one less degree of freedom. Okay, good. That was a quick version of stabilizing hybrid limit cycles.